Before we get into the mathematics that governs probability calculations, we're going to need to introduce a few key concepts. Since we'll eventually have to determine the probability of certain propositions being true, sometimes based on their relation to other propositions, it's important to get clear on what those important relationships are. And we'll do that by looking at a new way of representing these relations, Euler diagrams. We'll also determine how many possible options there are in certain circumstances, since that's relevant to their probability. And we'll cover some relationships the possible outcomes can have to each other. By proposition, I mean the set of circumstances that a statement represents. Remember from when we defined arguments that statements are declarative sentences that can be judged to be true or false. For our purposes, we're going to treat statement and proposition as essentially interchangeable, even though there is an important philosophical difference. Some of the relationships we covered from deductive logic, like equivalence, entailment, consistency, and inconsistency, will be relevant again for probability. Consistency, or compatibility, and inconsistency, or mutual exclusivity, will be the ones that are particularly important for understanding how probabilities work. Sentences are compatible when they can both be true together, and they're mutually exclusive when they cannot be true together. So we could use our original truth table method to represent all of these properties, but we're going to shift gears and we're going to look at an alternative way of representing them, and that's Euler diagrams. In Euler diagrams, the circles represent propositions, the situations under which each proposition is true. So here we have the diagrams for two of the properties we're interested in, equivalence and entailment. The left diagram for equivalence, where proposition A is equivalent to proposition B, is represented by these overlapping circles. The situations in which A and B are true completely overlap. So the two sentences are true in all the same circumstances. That's exactly what we should expect from what we know about equivalence from before. The right-hand diagram shows entailment. If A entails B, any of the circumstances that make A true also make B true. So we represent that with circle A falling within circle B. What this shows is that B may be true when A isn't, but all the circumstances where A is true have to be circumstances where B is true. So they have to be among the circumstances where B is true. We can also get Euler diagrams for compatibility and mutual exclusivity. On the left, we have A and B are compatible, and that's because there are some circumstances where both sentences are true together. So the circumstances where they're both true are represented by the overlap between the A circle and the B circle. Contrast that with the right-hand diagram showing mutually exclusive sentences A and B. We have no overlap between these circles because there's no overlap between the circumstances where each proposition is true. So if A is true, B is false, and if B is true, A is false. Again, these two concepts in particular will be relevant to our discussion of probability. What does probability do? It assigns likelihood values to different possibilities. Since that's how it works, it's useful to be able to determine what all the possibilities are. So here's some examples. With flipping a coin, we have two possibilities, heads and tails. With rolling our standard six-sided die, we have 6 possibilities. You could roll a 1, 2, 3, 4, 5, or 6. We also have some more esoteric ways of generating many possibilities. We can have sets of possible outfits that can be made from a red shirt or a white shirt, gray or black jeans, and white or black shoes. In this last one, we start with some compatible options. So a red shirt is compatible with wearing white shoes. But we have to determine all the possible outfits, which require a shirt, pants, and shoes. So these 8 final possibilities are all mutually exclusive, even though the things that made up the possibilities were compatible. So we built up these mutually exclusive possibilities from compatible parts of the outfit. Wearing a red shirt is compatible with wearing gray shoes, but wearing a red shirt with black pants and shoes is not compatible with wearing a red shirt, gray pants, and gray shoes. Why do we care about cataloging all the possibilities like this? Well, identifying all the possible options is important to determining how likely any one option is. And in order to describe all the possible outcomes and how likely they are, we need our set of possibilities to be a partition. A partition is a set of possibilities, which can be described with propositions, that meet 2 conditions. They have to be mutually exclusive, which we've already looked at. Each possibility has to be distinct. And they have to be exhaustive. So the propositions that characterize the partition describe all of the possibilities. Why do we care about partitions in the context of probability? Well, when we take a partition, the total probability of all the possibilities in it has to add up to 1. So take our example of a dice roll. We have a 6th chance of rolling each of the sides, and if we add up all of the 6, we get a total probability of 1. That, we'll see later, fits our definition of probability. Examples that we've looked at, like coin flips and dice rolls, have this characteristic of fairness. Each outcome of the roll of the flip is determined by a fair process. Fair process has these 2 features. The process is unbiased between the various possibilities. So that means that all of the possible outcomes are equally likely. And in a fair process, the event that leads to one outcome is independent of events that lead to any other outcomes. So let's think about what these terms mean in the context of a dice roll and why it counts as fair. It's unbiased because each side is equally likely to land facing up. And each roll is independent. So you roll a 1 on your first roll. That has no effect on what you're going to roll the next time. You're still equally likely to roll each side. When we have a partition of all of the possibilities of a fair process, we get to calculate the probability in a super straightforward way. The probability is the number of favorable outcomes, the one we're interested in, divided by the number of total outcomes. Since the partition captures all of the possible outcomes, we get the number of total outcomes from that. And since all the outcomes are equally likely, the simple ratio of the number of outcomes we're interested in to the total number gives us our probability. So again, let's go back to one of our examples. Let's say we decide to list all of those 8 possible outfits from our red or white t-shirt, gray or black jeans, and white or black shoes, and we put them all on a hat. So we've got our 8 options in a hat. What's the probability that we pull an outfit with gray jeans and white shoes? Well, we know that there are 8 total outfits. We already saw that when we listed all the possibilities. And then there are 2 outfits with gray jeans and white shoes. One with a red shirt and one with a white shirt. So that gives us a total probability of 2/8 or 1/4 for outfits that fit that description. Not all processes are fair, though. Sometimes the outcomes are going to be biased in some way. So a classic example would be a coin weighted so that it's more likely to land heads. This is biased because both options are not equally likely. The probability of landing heads is going to be more than 50%. A process can also be, quote, unfair if later outcomes are dependent on previous events. So dependent outcomes are ones where what happens in the next event depends on the previous ones. Take, for example, pulling a marble out of a pot with 20 blue marbles and 20 green marbles. We can pull out of the pot in two ways. We can sample a marble with replacement. That's a case where the outcome of each draw is independent because the number of marbles doesn't change. You take the marble out, you check its color, and you put it back. You still have 20 blue and 20 green. You can also sample without replacement. In that case, the outcome of each draw is dependent because the number of marbles of each type will change after each draw. When you take a marble out and leave it out, you change the total number of marbles and the ratio of marbles of each type. So the chance of drawing a blue marble or a green marble will be 50% on your first draw, but it won't be on the second because there'll be one fewer of either a blue marble or a green marble, and only 39 total marbles. From this lesson, you should get a flavor of the way that probability works before we enter into our discussion of the probability calculus. And the concepts from this lesson, like independence and fairness and mutual exclusivity, will be key to understanding how to calculate probabilities going forward.